Okay, we've got a 10 kilogram block released from rest at point B. So the spring is stretched out a distance 0.5 from its neutral position at A. Okay, got a coefficient of kinetic friction. Wants me to find the velocity as it passes through point A, and then the maximum distance the block goes. So because we're trying to find velocity at specific positions, we're going to use work and energy, where I've got the initial kinetic energy plus all of the work done equals a final kinetic energy. Okay, and I'll start with that initial kinetic energy, which of course is going to be 1/2 mv squared, but it's 0 because I believe, as it says, it is released from rest. So that is no kinetic energy initially. Okay, so now we got to talk about the work being done between state 1 and state 2. Okay, so the first thing we're going to talk about is the work done by a spring, which is going to be 1/2 ks squared minus the other ks squared. So k is 300. Okay, and then initially it has a stretch, right? Because I'm doing 1/2 ks squared, where s is the stretch in the spring. So initially the stretch in the spring is 5, and then at point A there, the stretch is 0, right? Because that, again, is the neutral position at A, okay? Now what we need to do is determine, is this positive or negative work, okay? And the way we know that is if motion is in the same direction as the force, then the work is positive, and that spring is pulling it to the left in the direction to the left. So the spring force and the motion are in the same direction. Therefore, that is positive work of the spring. Okay. The other piece of work done here, and maybe I should go through and draw a quick free body diagram here, right? So we've got the force of the spring, we've got mg, we've got a normal force, and then we've got a friction force, which is going to oppose that motion. Okay. Um, uh, so again, motion is left to right, so or from right to left. Motion is to the left. So now friction we're going to do next, okay, which is going to be mu k times the normal force. The normal force equals the weight by just summing the forces in the y direction. Hopefully that's pretty straightforward. So if that normal force is that, then my friction force is going to be mu k mg. Okay, so that's my friction force. Okay, that is also in the horizontal direction. So I have that friction force, which is mu k, which is 0.3 times the mass, which is 10. Okay, so that's the force. Okay, and that force acts over the distance of 0.5 meters. Okay, so again, it's force through a distance. Now the question becomes, is that positive work or negative work? Okay, and again, motion is to the left, friction is to the right. Those are in opposite directions, so I have a negative work being done here. Now gravity does no work because it's vertical and the motion is horizontal. Likewise, the normal force does no work because it's vertical and the motion is horizontal. So again, those do no work. The only thing that's doing work is the positive work of the spring pulling it to the left, and the negative work of the friction acting against that motion. Okay, so that's the work being done. The final kinetic energy, that's really what we're trying to find, which is going to be 1/2 mv squared, where m is 10 and v is what I'm looking for. Okay, so now we go ahead and go up to our top equation where we have 0 for the initial kinetic energy. Plugging in all the values for the work from 1 to 2, I get 22.8. Okay, and then that's going to equal 5v squared. And from that, I can find that the velocity, and this is at point A, becomes 2.14 meters per second. Okay, taking it a step further, okay, now I'm going to go from 2 to 3. Okay, because I want to find the maximum distance. So at point C, it's basically the velocity goes to 0, right? And that's where it no longer is moving to the left. So that's going to be the maximum distance. So my final velocity here will be 0. Okay, the work being done to this is going to be 1/2 ks squared again. Okay, but now I don't know that distance. That's why I'm trying to find x squared. Okay, again, initially I'm at 0. Okay, now the question is this positive or negative work? Now this time the spring is working against the motion, so it's actually going to be negative work, right? Because the spring is now pushing to the right, it continues to move to the left, so that's going to be negative work being done. Okay, the friction force looks the same, mu k times the mass times the gravity times the distance traveled, that will be x. And again, that's going to be negative. Friction's almost always negative. Well, friction is always negative, okay? Because friction, by definition, opposes motion. So if it's going in the opposite direction of motion, then it's got to be a negative work being done, okay? And again, as I stated previously, the kinetic energy at the final position is 0. That's going to give me that maximum displacement that I'm looking for, okay? So KE2, okay, is 22.8. We can get that from the previous equation. The work being done this time is going to be 1/2 150 x squared minus 29.4 x, and then that's going to equal 0. Okay, so again, this is KE2, this is the work from 2 to 3, and this is KE3. Okay, I can solve this, and I find that x is going to be equal to 0.304. Okay, so again, because I'm trying to find velocity at specific positions, I'm going to use work and energy. Okay, energy is 1/2 mv squared, and depending on what I'm looking at, I can plug that in. The work being done, I have two works. I have work of the spring, 1/2 ks squared. Okay, initially it's doing positive work. Once it crosses and starts compressing, it does negative work. The friction is always doing negative work. That's the friction force times the distance that it slides. Okay, and it's always opposing motion, so it's negative. We use those equations to calculate the velocity at point A and then the maximum displacement when it gets to point C.